Another type of special case of map projection is the conformal projection. With the conformal projection, what we see is that shapes are preserved so that everything in this map projection is its proper shape. As you may guess, what is not preserved is the size. So some things appear quite larger than they really are, especially at things as you move away from the equator. So right at the equator, because this is a normal cylindrical map projection, there would be no distortion right along the equator, but as you move further to the north and south, objects become bigger and bigger, even though their shape is being preserved. This type of map is often used as a world map, especially in classrooms, and it got a bad reputation for this because some people said that things at higher latitudes, such as where the United States and Europe are, were being shown larger because those were the most powerful societies. Whether that's true or not, this map projection really gained in popularity, but it was never designed for a world map in a classroom. It was developed in the 1500s by Gerardus Mercator, and what he was trying to do was find a way to plot lines on a map for sailors so that if they had an orientation such as they measured with their compass, they could just draw a line on a map, and that bearing or that rum line would be the direction that they're going. That was extremely useful if they knew their location and knew where they wanted to get to. So we can also, instead of doing a normal Mercator map projection, we could do a conformal, or a transverse Mercator map projection, which is also conformal. So instead of having the cylinder run north-south, now we have the cylinder so it touches along a line of longitude. And we wouldn't want to make an entire world map like this because it would be so distorted as we moved away from that one line of longitude that touched the cylinder. But we could make little slices of map projections, such as shown on the right here, by just taking part of that between two different lines of longitude. Of course, the distortion, especially of size, would increase as we moved away from that one line of longitude that touches the cylinder. So we would want to be careful of that as we move away, to not move away too far when we're making these little strips. If we looked at a conformal map projection of the United States, we could see that if the central meridian in the center of this map was touching there, then we would, if it were a secant case where it was cutting through the globe, we would have two lines of true scale. And we see that on the left-hand side and the right-hand side. The line of true scale is running through western Pennsylvania and Florida on the right-hand side, and the line of true scale is running through New Mexico and Montana on the left-hand side. And the distortion would increase towards the middle of the map, and it would also, once again, increase away towards the sides. So another type of conformal map projection we can do is on a cone instead of on a cylinder. And in this example here, this is a Lambert conic conformal map projection. And basically it means that we're first projecting onto a cone, and then that cone is being flattened out, and that's how we get the map projection. We can see in the example here, they're using two lines of standard parallel. That would be where there's no distortion because the cone is actually in contact with the surface of the globe. And we can see those on the map as the two standard parallel lines that are listed there. The distortion between those two standard parallel lines would increase as that top blue part is getting flattened down to the cone. And there would also be distortion away from those two standard parallel lines as things have to be stretched out in order to reach up to the cone from the sphere. These Lambert conic conformal map projections are especially good for places that fall in this example between those two standard parallel lines, such as Europe, China, the United States, and Russia. Those would be examples of good places to use this sort of Lambert conic conformal map projection. And places that wouldn't be good at all would be places close to the equator, such as Africa and South America. So going back to the Mercator, the transverse Mercator on the cylinder for a moment, if you think about that, we can use a standard parallel in the middle of the area that we'd like to map, and then we could just turn the cylinder a little and make our next map. And we could keep doing that at different lines of longitude until we went all the way around the globe. Each time we do one of these, if we just limit it to a certain width of longitude, then we would just kind of make a strip that looks like this. So each one of these strips is bounded by lines of longitude on either side. And of course, they all come together at the North Pole and the South Pole because that's where those lines of longitude pass. In doing something like this, we can make a series of little narrow maps, and then these can actually be pasted right onto a globe in order to make a globe. These type of conformal transverse Mercator map projections are sometimes called the gores of a globe, G-O-R-E-S for gores.